Hi, welcome to the live section of the data path lectures, and we will discuss the multiplication. Okay, so the multiplication operation consists of two operands, the multiplicand and the multiplier. And here's an example. We are multiplying the 25 multiplies 39, and the multiplicand typically is at the top and the multiplier is at the bottom. Then we perform the multiplication much like we have done with the multiplication of the decimal system that we learned in the elementary school. So we check the first bit of the multiplier, and if it is 1, then we copy the multiplicand. Then we go to the next bit and we copy the multiplicand, but shifted 1 bit. That's because this bit significance is 2 to the 1. And the third bit, okay, we copy after shifting this by 2 positions. The fourth bit is a 0, so we copy string of zeros. Fifth bit 0, string of zeros, and last bit is 1, and we copy the multiplicand shifted multiple positions to signify its appropriate position. Okay, then we add. Notice this comes down straight, this bit. Okay, and then we add 0 plus 1, 1. We add 0 plus 0 plus 1. This is a 1 here. And we add 1 plus 0 plus 0 plus 0. This is a 1. And we add 1 plus 1 plus 0 plus 0. This is a 0. And we have, this is the 0 here. Okay. And we have a carry of a 1. So 1 plus, okay, dokie, did we do, no, the carry should come over here. Okay, 1 plus 1 plus 1 plus 1, then this is 4, 0, a carry over 0, and a 1, okay, because this is 1, 2, and 4, okay, 0 plus 0 plus 1, 1, and then we have a 1 here from a previous carry, 1 plus 0 plus 0 plus 0 plus 0, it's a 1 here, and here a 1, 0, 0. So this group of numbers here, we call them partial products, and the final result we call it product. Okay, now, so this is basically the multiplication, and typically if we have the multiplier is so if we have the multiplier in or multiplicand in bit and multiplier in bit, the product will be a width of n plus m. But in reality, really, these two things, the multiplier and multiplicand, will be of n bits. Both have the same size. It is highly unlikely to have them different. So we'll say if the size of those n bit and n bit, and so the product will be size n 2n. Okay. All right, because the product, the multiplication grows the size of number of bits of the result. Okay, now, so having said that, if we express the multiplicand as these are the bits here, the collection of bits, and raised to 2 to the power. So this is basically 2 to the power 0, 2 to the power 1, 2 to the power m. And of course, y0 is multiplied by 2 to the power 0, y1 multiplied 2 to the power n, and this signifies the position of the bit. Similarly, the x, okay, and so the product is the multiplication of these two numbers, and basically we are trying to express this mathematically, and you can see that here is the multiplier, here is the multiplicand. We check the first digit of the multiplier, which is x0, and then we multiply it with all these bits of the multiplicand. So you can see it's x0, 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 multiplied by y0, y1, y2, y3, y4, y6. Then x1 is multiplied by y0, y2, y3, y4, y. Then x2 multiplied by y0, y1, y2, y3, y4, y5. Then x3 and x4 and x5. Then we add these partial products, all right, to produce the product, okay, like what exactly what we have done in the numerical example. Okay, okay, all right, and then we start adding those rows to get P5, P6, P7, P8, P9, P10, P11. Okay, all right. Now, so basically, we can see that how this x0 was of the multiplier was multiplied by a multiplicand, then x1, then x2, da 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 to x15. All right, if we have x50, 16-bit multiplied by 16-bit. Okay. Now, the question is how to implement a multiplier. And one of the techniques to implement a multiplier is something called the the array multiplier, and which is uses the carry save adders. We have seen the carry save adders in the data path part where we need to add multiple numbers, more than three or more numbers. So we use the carry save adders. So basically here, what we do is that, whoops, sorry. Let's go back here. So here, the array multiplier, you can see that the following organization, that I will send the x0 and the first array of these blocks, right? Okay, and those blocks, every one of them, watch, in every one of them, the very first one receives y0, the second one receives y1, y2, and then I send this is x0, then I send x1 to the same array of these blocks, shifted to the left by one position. All right, again they are fed y0, y1, y2, y3. Then the third row of these blocks, I will send to it as well x2. All right, and again they are fed y0, y1, and y2 and y3. Again, the array of these blocks is fed x3. Notice how the organization, how these are being shifted one position every single time. And this is to signify that this x3 is x0 of weight to 0, x1 of weight 2 to 1, x2 to the 2, and oops, 2 to the 2, and x3 has a weight of 2 to the 3. That's why I'm shifting these blocks. What's inside this block? What's inside this block is that I am multiplying the xi with the yj with just a simple AND gate. Then I'm receiving a sum from the previous row and a carry from the adjacent row. Then I'm producing a sum to the next row, and so this is here is a carry save adder, because I'm receiving 1, 2, 3 inputs, and I'm producing a carry out and a sum. So this is a carry save adder. And the last, once I finished the axis here, then whatever I provide in terms of sums and carries, I finish them off and I add, because there will be two rows of one for the sum and one for the carry. I add them with our conventional carry propagate adder. Okay, and this is the carry propagate adder is like so, right? This carry propagate adder, notice this, there is a propagation happening here, and this is a very slow adder. So the previous squares here, all of these squares are carry save adder. The last adder is the carry propagate adder. This is just slow. Okay, when this thing is optimized, I need n minus 2 carry save adders and 1 carry propagate adder, n minus 2. So in a multiplier 4 by 4, I need 2 level of carry save adders and 1. So one person might say, well, if you're saying 4 by 4, you need 2, but I'm counting here 1, 2, 3, 4 levels. But the formula says n minus 2, and I should see two levels here. The reality is that you can really optimize the very first 3 rows into just a single row, because there is no sums coming from the top here, okay, or carries from the adjacent, so you can squash them into just one layer after certain optimization. So the optimized design typically requires n minus carry save minus 2 of carry save adders and CPA one carry propagate adder. Okay, all right. Now, this layout can be put into a square. He just kind of rearranging the inputs and the output to make it look like a square. And in VLSI design, we like square designs because they are easier to implement, or a square or rectangle rather than diagonal. Okay, now we saw this idea of adding the partial product, which is a headache, and now we're trying to reduce a number of addition of these partial products, and this is the idea of Radix-2 booth recording. See, Booth was involved in optimization and of the multiplier, and they used to use the serial multiplication. Basically, check on the bit if it is a one or a zero. So a one triggers an addition, and a zero there is no addition. So Booth, what tried to do in the early multipliers, he tried to reduce number of additions. Okay, so he noticed the following. He says in a series of a 1, so if this would be the multiplier, if this number is the multiplier, notice here we'll check on a 0, nothing happened. Here is an add, triggers an add, triggers an add, nothing happens here. Okay, so these three numbers of ones will trigger addition. Booth said, I can re-express this number in a different way. Okay, so he noticed that this number is and the like, this special series of ones, equal number 14. Now, this can be expressed as 16 minus 2. And notice 16 minus 2 can be written something like this. A number will be like this: 1, 0, 0. All right. Let's see. Minus 1 and 0. So one might say, what is this? I would say this is a booth recording digit. In booth recording, we use 0, 1, and minus 1. Okay, what does a minus 1 mean? It means a minus 1. So how can we code this in binary? Well, we have to use more than single bit to represent these digits. Okay, so you might want to choose you will need to choose two binary digits for these booth recording digits. So now if this would be the multiplier, this would trigger nothing. This will trigger subtraction, nothing, nothing, and addition. So now you can see, while this one will trigger three additions, this will trigger just one addition and a subtraction, a saving of one addition. Okay, and I'm talking about this number being the multiplier. Okay, now how can I convert this 0, 1, 1, 1, 0, which is the binary number, into booth recording? We'll have to use something like this table. Okay, so what we do is that we start off by adding a oops, that's not what I want to do. Okay, let's go back, and we start by adding this phantom digit here, which is a 0, and the most significant, next to the most least significant bit here. Once I add a 0, then I group the numbers in twos. So I look at 0, 0, and then I come to this table and say 0, 0 is encoded by what? By a 0. So this is a 0. Then 1, 0. 1, 0 is encoded by what? By minus 1. Minus 1. And then 1, 1 is encoded by 0. And 1, 1 is encoded also here by 0. And 0, 1 is encoded here by a 1. So now notice that this is now This is my booth Radix-2 booth recording, or booth encoding. Okay, so this is -1 here. Okay, so now I converted this number into booth recording. Let's use this number as the multiplier. Okay, so I've used this number to do the conventional multiplication, and you can see how this number 1 triggered this, and this number 1 did this, and this number 1 did this. So I have to add 3 rows of digits here. Now let's see both recording what it did. So here is 0, so this is the 0, and -1. Okay, what's a -1 here? I take the 2's complement of this, and the 2's complement of this is 1, 1, 1, 0, 0, 1. Okay, 0, 0, 1. And I stop here. No, don't stop. Add extra ones. We call it extending the sign. If you don't extend the sign, your addition of these rows will be wrong. If your number is negative, do not forget to extend the sign. Okay, and then a 0, we get this, and then 0, we get this, and then the 1, we get this. Okay, and the 0, we get this. Then add. We add them, regular addition. Okay, and I get this number, which is exactly this number. Okay, notice this one here. If you want to evaluate, this number is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So this is 1 multiplied by 2 to the 4, which is 16, plus -1 multiplied by 2 to the 2 minus 2, and this is equals 14, which is equals the value of this digits, which is 14 here. Okay, so notice here I have 3 rows which are non-zeros. Here I just have 2 rows. I reduced number of addition with using Radix-4. So Radix booth encoding, what it does, it tries to reduce the number of rows which are non-zero. Now, then people took this concept and went into higher level of Radix modified booth. And what the people did, they invented method which is Radix 2 to the I, okay, where I can reduce. Let me use the whiteboard. So suppose I have this number of rows for partial product n. So I multiply two numbers, every multiplier and multiplicand, multiply the two of them, and these are in rows of partial product. Okay, now and then I add them to get the final product. So this n row, I can reduce this n by n to the I, meaning when I multiply two numbers, n times n, I'll get here these number of rows will be their number will be n to the I, n divided by I. When I use Radix 2 to the I. So basically, if I use Radix 4, and 4 here it is 2 to the 1. I'm sorry, 2 to the 2. It means I can reduce the number of rows by half, which is good, because what is really slowing the process is what? It is these number of rows. So instead of adding 60 rows, if I can add 8 rows, will be good. If I just need to add only 4 rows, will be even better. So the idea, I'm trying to shrink this. So Radix 2 to the I, what it does, it reduces number of rows from n to n divided by I. Okay, so now, so Radix 4, and 4 here equals 4 here equals 2 to the 2, which means I can reduce number of rows from n all the way to n over 2. Beautiful. But now our encoding will be a little harder. We have to look at 3 bits from the input, okay, to produce one digit, and the digits are now more complex. We have 0, we have 1, we have 2, we have -2, we have -1, right? So more complex digits, okay, but we can live with those. We can live with those. Let's take an example here. Suppose I have this number, hex number, which I can represent in binary like so. Okay, so this is the binary representation. I want to convert this to Radix-4 Booth. I'll use this table right here. So here's what I do. I'll add my phantom 0 right here. Do not forget, next to the least significant bit, always add a 0. So this is the 0. Then what I do, I group 3 bits like so, 3 bits like so, like so, like so. Okay, I did a mistake here. I need to erase. Okay, that. Okay, so let's go back, and so I'll do this, and 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 this. Okay, now once I group, notice the overlap at the boundary. Also, notice at the center there is a digit which is not overlapped. This is not overlapped. This is not overlapped. This is not overlapped. Not overlapped. Why am I focusing on this? Because this is going to be the weight of the digit that I'm producing. The weight of the digit. So let's take a look at these 3 bits. This is 1 0 0. Okay, 1 0 0. Let's get another color here. Whoops. Let's get another color here. Let's for example take a green. So 1 0 0 0. Let's go to the table. Where is 1 0 0 0? 1 0 0 0. I have a digit of -2. So I plug in here -2. Okay, what is the weight of this digit? We multiply -2 by the weight of the center digit. This center digit has a weight of 2 to the 0. So the weight of this digit is -2 multiplied by 2 to the 0. Beautiful. Let's go to the next 3 digits. These are the next 3 digits. 1 1 1. Let's go to the table. 1 1 1 1. It gives me -0, which is exactly 0. So here is the 0. What's the weight of this 0? We look at the center digit. What's the weight of it? So the value of this digit is 0 multiplied by the weight, which is right here. Okay, let's take a look at the next 3 digits. 1 0 1 1 0 1, which is right here. 1 0 1. This is -1. Of course he's using the y, which is kind of confusing, but okay, so this is -1. Okay, so what's the weight of this digit right here? Look at the center bit here. The weight of it is 2 to the 4. So 2 to the 4 multiplied by -1. Continue doing and producing all these digits. If you multiply them the correct way, you will get 23,982, which is the value of this hex and the value of this binary number. So this is so now the Booth encoding the digits is 1 2 -1 2 -1 -1 0 and -2. Okay, all right, beautiful. Now let's take an example here. He's trying to do a multiplication of this number 25 and a multiplier of this number as well. The very first thing that I need to do is to convert this number here into what? Into recording, into Booth recording. So 1, this is the multiplier, 1 0 0 1 1 1. Okay, so very first thing I do is add that 1, which is the phantom. I'm sorry, add that 0, which is the phantom 0, which is next to the least significant bit. Then take 3 bits, 1 2, right? Let's see if I got those right. 1 2 3. Okay. Now One thing important, if the last period stops at a 1, which is like here, I add extra 2 zeros. That's by the algorithm. If you stop at a 1 in the last period, add 2 extra zeros and add one more digit here, because you should never stop at a 1. So we added these 2 extra zeros. Now if you look at this table, this is -1, this is 2, and this is -2, and this is 1. Okay, so these are the digits for the booth encoding. Can I check them? Yeah, you can check them. You can say here the weight of this is 2 to the 0, 2 to the, and you add them up, and you should so this is 2 to the 0, 2 to the 2, 3, 2 to the 4, 2 to the, okay, 2 to the 6. So 1 multiplied by 2 to the 6, which is 64. All right, so 1 times 64 plus -2 times 2 to the 4, which is 16, plus 2 times 2 to the 2, which is 4, plus -1 multiplied by 2 to the 0, which is 1. You add all of these guys and you should get 39. See, 64, 32, 32, and 7, you get 39 exactly. Okay, now we need to multiply this with the multiplicand. Now when we do the multiplication, right, we're basically, now we have the multiplicand, which is 0 1 1 0 0 1, multiplied by the digits of the booth, which is -1, 2, -2, and 1. So the very first thing is that I multiply this digit -1 with the multiplicand. -1 with the multiplicand, it means 2 complements. So this is the 2's complement of the multiplicand. Watch. The 2's complement is 1 1 1 0 0 1, and this is excuse me, this is extension of the sign because it's negative. Then this is 2. Now watch what we have. When we drop the digit, we shift the answer 2-bit position. In other words, I don't start by just shifting one position. No, we shift 2 positions, because this is Radix-4. So we shift 2 positions. Then I write my answer, which is right here. What's my answer? It says we should multiply 2 times the multiplicand, which means the multiplicand multiplied by 2, which means shifted to the left by 1 position. So this is a shift to the left. We shift it to the left by 1 position, 0 1 0 0 0 0. Then -2. Okay, notice we leave 1 position, 2 position. Then we have our answer of -2, which is the 2's complement of this. Take the 2's complement, 0 1 1 1 0 0, or you take a 1's complement and then you multiply it by 2. Okay, then 1, which is the same as the multiplicand. Watch, empty, then I write my answer, which is here the multiplicand. Then add the bits. Notice how many rows I have, just 4 rows. Notice how many rows I have. These are 6 rows. Okay, supposedly I should get n over 2, but certain, this is when I use numbers like 8 bits multiplied by 8 bits, or 16 bits multiplied by 16 bits. But since I'm using 6 bits, I'm getting not the best number of rows here. Like, okay, so, but for example, look at the number here. How many digits I have? I have 1 digit, 2 digit, 3, 4, 5, 6, 7, 8 Radix-4 digits, right? How many binary bits I have? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 binary bits. I was able to express them in 8 Radix-4 booth encoding digits. And so from 16, here is 16, oops, sorry, These are 16 and these are 8 digits. And as I said, if you use multiplication with this, you will create, if this would be multiplier, you will get 16 partial products. But if I use this recording here, I will get 8 partial products. Okay, now here someone, as again, I'm using here a size of 6 bits, which is not 4 or 8 or 16, so you get close to n to the 2 divide by 2 rows. Okay, all right. So finally, we look at these rows here, okay, and the representation of these partial products, 0 or digit 1 or 2 or -2 or -1 and -1 or 0. Kind of these are the Booth digits. How are we representing these in hardware? Obviously, I need more than one bit to do it. And one way to do it is to use a bit that says single, meaning that if you have a 1, watch, if you have a 1, then you activate this bit. You see, if you have a 1, you activate this bit. Or double, which means if you have a 2, you activate this bit, right? If you activate. And a negative, these are turned on whenever you have what? Negative values. Okay, so the way we express these digits is using these 3 bits. Okay, a single, active when you have 1, a double, active when you have a 2, and a negative, active when you have a 1, when you have a negative number. One thing you should notice that I have 2 zeros, a +0 and a -0. This is a caveat of the Booth encoding. Okay, so this is how you represent the Booth coding digits. Okay, with that, we conclude our lecture about Booth multiplier, and thank you very much.